All right, so as Chad said, my name is Russell Vernon. I'm an application engineer for Solid Thinking, and what we're going to talk about today is how to create radically better products with design optimization and 3D printing. So we're going to start off with a few slides explaining our Solid Thinking products, both Inspire and Evolve, and then we're going to go into a specific application we did with Exact Engineering, a design consulting company, on an example where we used Inspire and Evolve to metal print a lighter, stronger structure, specifically a bracket. So we're going to actually go into the tool, go into Inspire and Evolve, and show that process as well. And also, I wanted to mention, if you have any questions while we're going through this webinar, feel free to ask them in the chat window to your right. And at the end of the webinar, we'll have a little Q&A session there and answer those questions in the question box. So feel free again as the webinar goes to ask questions there, and we'll answer those at the end. All right, so first I want to talk about Inspire. What Inspire is an upfront concept design tool that was developed for design engineers and designers. And what Inspire does, it allows design engineers or designers to develop products faster, smarter, and lighter. And when you use Inspire in the concept design phase of a design, you essentially arrive at your optimal solution early in your design cycle. So you're able to know right off the bat where material should and shouldn't be, or the optimal placement of material in the concept design phase. So you're starting from an optimized shape rather than going through design through trial and error and bouncing designs back and forth between analysis teams and design teams to arrive at that solution. So essentially you're arriving at this optimal solution earlier in the design phase and reducing your product design time. Inspire also enables designers to have smarter designs. So Inspire uses a powerful topology optimization solver in the background to develop these organic shapes, and essentially it's based on the way nature would move material around to accommodate loads. And again, the solver has been around since the 80s, and it's been established in a lot of major OEMs as well. Until recently, we've rolled this out to designers to have this capability to optimize shapes early in a design. So that's how you get a smarter design. And lastly, lighter design is Inspire helps you when you know exactly where materials should and shouldn't be based on the loading applied to a part. You get a lighter design, so you know exactly where to put material. And when you know where to put material in the optimal fashion, you arrive at your lighter solution. And the way Inspire works is you assign it a packaging space. So in this brake pedal example on the screen, the packaging space, we call it the design space, is all the region or that volume where that structure is moving. And what the design space is we're telling Inspire exactly where Inspire has a freedom to move material around to accommodate those loads. And then the other side of that is assigning your non-design space. And your non-design space are the areas in your design you want Inspire to retain. So for instance, the gray areas in this brake pedal where the foot actually hits the brake pedal and where the brake pedal attaches to the car, you have a non-design space area. Inspire is still going to analyze those, but we're just telling Inspire not to touch those areas. Don't move material around in those areas. So when you assign your packaging space, and then as well as your loading conditions, Inspire will quickly generate this ideal shape. So this shape that's created is essentially your optimized solution, and it's meant to run in minutes, not in hours. And we'll quickly see all this this process when we go actually in the tool for this application we're going to talk about later. And one last thing is Inspire runs on both Mac and Windows. The other tool we're going to talk about is the Evolve tool. And what Evolve is a high-quality 3D hybrid modeling and rendering environment that enables industrial designers to evaluate, research, and visualize various designs faster than ever before. So what Evolve does is allows you to quickly create these complex organic shapes that essentially Inspire creates. It allows you to design those in a hybrid modeling environment, whether you're doing surface modeling or solid modeling or polygonal modeling. Inspire or Evolve combines all three of those modeling techniques to allow you to quickly recreate these designs and do your surface modeling. And what I'm going to show you today is how we combine both of those tools together to create this organic shape that was metal printed. And Evolve, as well as Inspire, they both run on Mac and Windows. And real briefly, I wanted to go over some examples where we have used both Inspire and Evolve in the real world. So this was an antenna bracket from Ruag. And what we basically did was we wanted to come up with the lightest solution that had a certain eigenfrequency associated with it. And not only did Inspire give us this optimal shape, we used Evolve to quickly create this optimal shape that was then printed. And this final bracket that you see to your left had a 43% weight reduction. And with that weight reduction, we had increased eigenfrequency properties as well as static behavior, strength, stiffness, and stability. So because of the orientation we move material around, or at least the way we designed this, it allowed not only weight savings but also property increases. So it is possible to reduce weight while increasing your strength and stiffness. And here's kind of a summary of some other projects we've done. There's the one on the top here is with Hardmark, and this was a 3D printed piston that was printed in titanium. And this is an example you can kind of see in the small area there. We used Inspire to come up with an optimal design. So Inspire showed us where material wanted to naturally be based on those loadings on the piston. We checked that design inside of Inspire to see if that was feasible. And then we redesigned that in Evolve to come up with a piston that was 25% lighter. And then you can see several other examples. So you can see the Ruag example, and also a few different aerospace brackets as well from LZN and AP Works, where not only was Inspire used for the optimization, but with the modeling, we're able to, with 3D printing, let's say we were able to reduce weight by 75% and 26%. So with that said, let's look at this specific example here with this aerospace bracket. And this was a project done with Exact Engineering and their design consulting company. And what they had a scenario where a customer wanted to 3D print a bracket used in aerospace. And what needed to happen was we wanted to take full advantage of the complexities that 3D printing can unlock. So some of the problem statements with this bracket, and we'll go into this bracket in Inspire and Evolve as well, but some of the problem statements here were, again, we needed to redesign a bracket to mount a sensitive component to a structural interface. So this bracket not only needed to be light and strong, but it needed to be stiff because it actually held a sensitive component on it. This bracket needed to be as light as possible, given it doesn't displace a certain amount. So I'll show you how that looks in Inspire. But pretty much due to gravity, we couldn't have this bracket displace this sensitive piece of equipment by less than 15 thousandths of an inch. And also the first natural frequency had to be above 250 hertz. So that was another problem statement we needed to design around. The original bracket that was being used was 0.17 pounds. The first natural frequency was 225 hertz and 1,000th inch sag, as described earlier. So we needed to really drastically improve those properties. And that's where we went to Inspire. And let me hop out of here real quick and jump into this problem statement. We're actually going to walk through how we did this in Inspire. So here is the Inspire interface, and you can see all of these icons on the interface are very simple, intuitive. We have all our geometry operations where we can create new geometry or edit this existing geometry, simplify it. And then we have our structure tab where we have all of our assembly tools. If we had an assembly we wanted to optimize, or set up our loads, materials. So we have a few different tabs here. And on the screen you can see we already had this design space defined. So the customer defined where material can live in their design. So based on their surrounding application, they knew that this design had to be within this volume here. And also we knew exactly where that mounting equipment needed to be. So this was this XYZ location. That's represented by this concentrated mass, 1.3 pounds. So this concentrated mass is in the location where it needs to be, and we know exactly where the design can live. So with this input, we were able to set up this model fairly quickly and see what the optimal shape would look like. And the way we did this, we can use the simplify tools, whether we want to remove imprints or rounds. In this case, I use a tool called a plug. And what plug does, it allows you to fill in holes or voids with the new material. And the reason I'm doing this, I'm going to use this plug tool to create non-design space regions. So I'm just clicking on all of these holes. This is where that piece of equipment mounted to the bracket. So now we have 4 non-design space mounting locations, and also I'm going to plug these bottom feet area, and that's where there was a fixed, where this bracket was actually fixed to the ground. So now what happens when I look at what we have here, if I hide my design space, you can see there's non-design spaces exactly where the mounting locations are. And in general with Inspire, it's good practice to have non-design space regions where connection points are, where loads are applied. So the next step, we have our geometry defined, we have our design space, we have our non-design space. Now it's time to set up our actual loads and load statements. In this case, there was no forces or torques or pressures involved. Is merely just gravity acting on this bracket. So we do have the ability to apply forces, pressures, torques, but what we're going to do is just connect this concentrated mass to these 4 mounting locations. The way we do that is with the connectors tool. So I can double click on this mass, click on connect concentrated mass, and now I'm just able to rigidly or flexibly connect this concentrated mass to these 4 mounting locations. So now essentially what I have is this concentrated mass that's connected in the 4 locations it needs to be connected to. And lastly, we need to prevent this bracket from flying all over the place. We need to mount it fixed in those 4 locations down here. So I click on the supports icon, and I can apply my supports to a face, to a line, to a point, or a cylinder. But in this case, I'm just going to fix these 4 mounting locations here. In general, that's your model setup. We just had one load case where we had gravity acting on this. And if we wanted to, on the left-hand side of the screen, you see load case 1. We can have, let's say this bracket experienced a 3G load in the positive Z direction or negative X direction. So you're able to actually separate all your loading conditions into loading cases where you can find one optimal shape that satisfies several different loading conditions this bracket would experience at different points in time. But in this case, we just had our gravity acting on this concentrated mass and then our fixed mounting locations here. Some other options with Inspire, again, if you had an assembly you're working with, you can apply fasteners, joints, and contacts. We can apply our materials. So in this case, we can have everything steel or change it to aluminum. So we have a basic material library. If we wanted to, we can create our own material where we just identify an E, a new, a density and yield stress, and a new material will be created. Some other features, our displacement constraints is actually what we're going to apply here. And what displacement constraints do is we tell the optimization, we tell Inspire that we want to create a design that prevents displacement past a certain bound. So in this case, we knew the furthest mounting location of this bracket could not displace more than 15 thousandths of an inch. So what I can do is go to this displacement constraints tool and click on this furthest mounting location here. And I'm just telling Inspire within this the sphere here, this mounting location cannot displace more than 0.00015 inches. So now what happens is you'll get the lightest possible design that satisfies all the constraints you set, but Inspire is gonna make sure that this mounting location stays stiff within that bound, so you can actually see the sphere there within 15 thousandths of an inch. So it's a way to get light parts, or at least the lightest possible material distribution that is also stiff in areas that need to be stiff. Some other features we can have is we can force symmetry on a part, where we can force a part to be symmetric or cyclic in any way. And also we have manufacturing constraints. So if you were not 3D printing this part and you knew you were going to machine it or cast it, you can tell Inspire to come up with an optimal shape, but make sure it's castable in one direction, or the single draw direction, or split draw direction, or even extruded. So you're able to apply these manufacturing constraints to accommodate whatever manufacturing process you're using. But in this case, this is going to be 3D printed, so we're not applying any manufacturing constraints. We're letting Inspire come up with the ideal shape that's unconstrained from a manufacturing standpoint. The next step here is to optimize it. So what we do when I click on Optimize, there's two objectives. We have maximize stiffness and minimize mass. When you're maximizing stiffness, you're going to essentially get your load paths, and Inspire is going to show you based on a mass target. So in this case, the default's 30%. Inspire right off the bat is going to get rid of 70% of the material, only keep 30% of this design space, and with that 30% material that's left, it's going to move this material around in the most optimal fashion to create the stiffest possible design. And again, that's going to show you your load paths. The other objective is minimize mass, and now with minimize mass, instead of being constrained from a material standpoint, you're constrained from a stress standpoint. So you tell Inspire that give me the lightest possible part that is staying within a safety factor of 1.2 or whatever safety factor you're working with. In this case, that's what we're going to use. Some other constraints in addition to your minimize mass or maximizing stiffness are your frequency constraints. What you can do is either maximize all frequencies. So let's say if you're maximizing stiffness, you can come up with a design that's stiff as possible and that has all natural frequencies as high as possible. Or in this case, since we're minimizing mass, we can say, give me the lightest possible design that stays above 250 Hertz. And we can apply those to certain loading conditions. In this case, our load case 1. So now what's going to happen, it's going to create a part that's light and stays above that frequency. So that's another constraint for our design. We can also apply thickness constraints where we can apply a minimum thickness, and really that's the resolution of your design, or how detailed you want Inspire to come up with this design. And that's the minimum member that's going to be created. So 0.1 is generally a good number, and with this, the smaller number you have here for a minimum thickness, the more detailed you're going to have in your design, but you're going to increase your runtime if that's too small. We have some other detailed parameters, speed and accuracy, and contacts if we're doing an assembly. We know gravity is going to be applied here, and it's going to be in the negative Z direction. And from here, we're ready to run. So with this, I have this model ran already, and what I'm going to do is just pull it up and show you what the results look like. So this is really what Inspire comes up with. You can see how it's set up. I actually set up the frequency above 200 with this one, just so we can better visualize the result. But so you can see Inspire comes up with this organic shape. You see your natural frequencies of this created design right off the bat. And also another feature you're able to see with this result that Inspire gives is our analysis. So at any point, Inspire can come up with this concept or the shape, and you can see if the shape's even going to be feasible from a stress standpoint or displacement standpoint. So you could run an analysis on this concept without having to take it out of Inspire and redesign it and then run it through your FEA solver. Instead, Inspire uses the loadings that were used for your optimization, and you automatically have a FEA ran, and in this case a modal analysis as well. Since there was no loads, we just did a modal analysis, and you can see all the natural normal modes as well. So with this shape, we're able to get a good idea how we're currently performing. So those are all options here. So the whole point of this analysis tool at the end of Inspire is to verify if this design is feasible. And then from here, that's your last step. Now that we have this shape, let's say we like the FEA results and we want to move forward with this design. That is where Evolve comes into play. So this design can be great, but if you can't model it, it's really pointless. And what we can do is take this straight into Evolve. So if I highlight this model, I can right-click on it. There's an option inside of Inspire that's called Save to Evolve. So when I do that, I bring in my model, and I'll just show you Evolve here. So I bring in my model, and you get the STL, or at least the outline of what the Inspire result was. And I believe this was a previous this was the previous design that was at a frequency of 250 hertz. So you can see this was our final design, and what we want to do in Evolve is really recreate that design, make it something 3D printable. Because if you notice inside of Inspire, we have lots of tessellated surfaces. So if I zoom in here, you can see all the tessellated surfaces, and that wouldn't be ideal if you were 3D printing as well. And so with what Evolve does, it combines a surface modeling environment with a solid modeling environment, as well as a polygonal modeling environment to help you create these designs quickly. So I use strictly polygonal modeling, and if you look here, I've created all these little polycubes. And what these polycubes are, if you're familiar with polygonal modeling, these are all converted to NURB surfaces right by a click of a button. So what I did, I just started with one cube, and you can see it down here. And I can edit points, I can edit the edges of it, or the faces. And what I did was actually just extruded multiple cubes around this shape. So here I'm just following the design of our optimization, and I'm just recreating this shape. And you can see how this looks in a NURBS curve form. And I could also edit it in NURBS curve form. But what I did was start from each foot here inside of Evolve. I created all these little cubes, followed the design, I stretched them, so at any point I can come in here and say, you know what, I need this to be fatter, smaller. But in general, I just followed the shape, and then I was able to connect them all. So with the Connect Faces tool, I'm able to say, you know what, I want this face here to connect with this face here. And then after just aligning the points, now I have a bridge surface. So really, generally, that's a process I use. I followed this shape. And then in the end, I came up with a design that looks something like this. So here you can see the organic nature of using that polygonal modeling system, or that polygonal modeling tool. And then from that poly model, I was able to do some of my solid editing tools. So I'm able to cut flat faces where I needed flat faces, or create my whole cutouts or counterbores. So that's what I mean by the hybrid modeling environment with Evolve. I have this organic modeling technique where I'm using these polycubes to create this, and then I'm able to combine a solid editing tool to create flat surfaces and create parametric holes and things like that. So from here in Evolve, I'm able to see a quick render of how this is looking. So inside of Evolve, there's a quick rendering tool where I can say, you know what, this is going to be a metal. I'm going to click here, apply a metal to it, and I just get a quick idea of what this part's going to look like. And again, that's where Evolve fits well in a concept environment. So now I get an idea of how it looks. I can do a quick render if I want, and it just gives you an idea of how this part's going to look when it's printed. So inside of Evolve, there's not only the modeling environment, but a quick rendering environment as well. So you can see the design here. And from here, I'm able to export this. Since Evolve's based on Parasolid, I can export it as a solid, Parasolid if I want a step. All the neutral CAD files, or since I know I'm going straight to printing from here, I can export this as an STL for print. So looping back to our presentation, let me come back here. There was two different routes that were gone through with using Inspire. So we came up with this Inspire result, and at Exact Engineering we kind of took two routes. We took one redesigning this part in Evolve, and then another route was redesigning this part in SolidWorks, just to see if there's some time savings involved and what the two different designs would look like. So we worked in parallel, and this design that you see on the screen is a SolidWorks interpretation of those Inspire results. And this part weight, again, with using Inspire and SolidWorks, still we were able to achieve significant weight savings, and come up with an ideal shape. And then taking it further, when I worked in Evolve, we were able to come up with this design like I showed you earlier. You can see how the performance properties are very close, but the one that stands out the most is our design time. In Evolve, using that quick poly modeling sketching system, I was able to come up with this design very quick and really a day's work. While in traditional CAD, typically you don't have that freedom when coming up with these complex shapes. So you can see comparing the two designs, they're both similar in frequency, stresses, displacement, and weight savings. Just design time was significantly decreased when using a tool like Evolve for your quick concept modeling. And these brackets were actually printed, so we used 3D Systems machines to metal print these, and in the end, this was the final part and how it looked. So with this 41% reduction in weight, we had a finished part now that was designed in less than a day. So with that being said, I'm going to pass it over to Chad, and we could possibly answer some questions you guys had.
Sure. So thanks everyone for any of your questions that you've asked already. And as Russell mentioned, if anyone has additional questions based on his demo or presentation, please feel free to ask those now. The first question, Russell, is, as we can see, this bracket was printed in aluminum, but is there a way to define different materials in Inspire? How do you do that? Can you show us?
Yes, good question. So inside of Inspire, we have a materials tab. So up here in the materials tab, you can change each part in your assembly. So again, we have different parts because we have aluminum, we have our non-design spaces here, and we have our design space as well. So each of these parts can have a material assigned to it, and we can change real quick between our material database. So in the material library, we have all those materials, or we can create our own materials. And also, with our new version of Inspire in 2015, we're able to link a material database to Inspire. So if your company uses a common material library, you can link that material library to Inspire. And on that question, it's also good to note that if you wanted to explore different materials, so let's say you didn't know what material you wanted to work with yet, but you wanted to see how the designs varied from material to material, that's the beauty of Inspire. You can have this quick iterative process where you answer these what-if situations. So what if this was an aluminum bracket? What if it was plastic? How would the design change? So just by changing those materials and exploring all those different designs, you're quickly able to see those differences because of the quick run times. So I hope that answers the question.
Awesome. Thanks, Russell. The next question is, can Inspire be used to design for traditional manufacturing? So maybe you can show us some of the design and shape controls.
Sure. So with this, the way shape controls work, so let's say if we were not 3D printing this bracket and we're looking to, let's say, cast it or machine it, you can apply these shape controls. And when you click on them, we have our single draw, split draw, and extrusion. And the way it works, a single draw, since this is one common part, it's maybe not as clear, but let me cut it up real quick just to make it a little more clear here. 1 second. Okay, so let's say we're looking to machine this, and now I have this thing broken up into 3 different design spaces. What I can do is apply these shape controls to each design space. So with single draw, if I click on one of these design spaces, this would make sense for a casting direction. So I can go in this direction. So this means Inspire will still satisfy those constraints I applied earlier, but it's going to make sure this is a design that a casting or mold would be able to be pulled in that direction, where this arrow is facing. And we can apply those in any directions. So in this case, I can apply it to multiple design spaces as well. So it'd be a casting that's being pulled from all of these different directions. Another option is split draw. So what split draw is, it's the same thing as your single draw, but now you have a design that a mold can be pulled in each direction. And that would be, again, a casting, or even I think of it as machining, where a tool can go in and out. So if this part was to be machined, this is how I'd set it up, and I'd rerun this optimization where it would come up with a design rather than that organic internal member type shape. Now it's going to be something that's where a tool can get in and out of all these three faces of this design. And the last one is extrusion. So what extrusion is going to look like is a common cross section. And let me do the last one here. So this cross section is going to be constant throughout this plane, whichever one you assign it. And this really helps define your ribbing pattern. So if you're looking to apply ribbing to a part to increase stiffness or anything like that, extrusion is great because it's very clear where the load paths are or where structural members can be placed. So you're just going to constrain those results where they don't taper on that plane. And again, that helps you accommodate your manufacturing process.
All right, thanks, Russell. And this one isn't a question, but this is just a really nice new feature in Inspire. Russell, can you maybe talk about the fasteners and connectors?
Sure.
And contacts?
All right. So let's say with this design, we knew it was bolted to a plane. Let me just delete these, just to show a quick example. So with Inspire, you're not really limited to just part level optimizations. So let me I'm just going to sketch this real quick. I'm just going to create a general big plane that goes through the whole part. So if we had like let's say a part that this bracket was bolted to, what we can do is go to the Structure tab, and actually let me go back here 1 second. Go back to geometry. Let me create these a little cleaner so it's a little more visual. I'm just creating some through holes here just to show how two parts would combine. And let me do a Boolean cut real quick. All right, so let's say we had two parts that were here. We have this bracket that's going to bolt on to this piece here. What we can do is actually keep this piece in the optimization without having to get rid of it. So what we can do, if we go to the Structures tab, I can click on Fasteners. What Fasteners does, it finds all lined holes or single holes. So here, I created those holes on the bottom, and it'll create a fastened connection as if a bolt would be modeled. So here I'm clicking all of these fastened holes, and you can see the representation of a screw. So what that does is it mimics how you would model this in FEA space as far as how a bolted connection would be modeled. So it more accurately captures from an assembly level how loads are transferred through parts. So if you have multiple moving parts or bolted parts together, you can apply fasteners, or if you had two parts that hinged upon one another, it works the same way. You can have joints. So let's say if I delete this fastener here, click on joints, I can actually pin two parts together. So if I wanted to, I can make sure this hole and this hole had a pin connection to it. Wouldn't really be applicable, but you can imagine if two parts had a pin connection. And with all these parts, you can have a screw connection or a bolted connection as well. And with the pin connections, you can have a collared pin or a pin or a sliding pin as well. So with that said, that's how you connect two parts to one another. And then lastly, you can see the interface between these two parts. So the way this bottom block interacts with this top bracket, the areas in green are free to slide, and those are their contacting surfaces. And then if we wanted to, if we said, you know what, these are bolted together, but they're bonded. There's no sliding contacts between them. So you're able to come in quickly and identify contacts between two parts. So this tool, it really helps open up possibilities with your designs. So it kind of opens it up from not just a part level optimization. Now you can apply a full assembly and see how loads are transferred through parts. So that's how the fasteners, joints, and contacts work in relation to your assembly optimizations.
Awesome, thanks, Russell.
Mhm.
So I don't see any other questions. We can stick around for another couple of minutes here if any last-minute questions do come in. But if not, thank you once again, everyone, for joining us today. Thank you, Russell, for the great presentation. And we will talk to you all very soon. Thank you.